Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we are starting a new section by diving into partial differentiation. We'll be introducing what partial differentiation means and looking at some associated definitions. So if you're ready to learn, then let's get into it. To start, let's consider u, which is a function of x and y, where x and y are independent variables. We can think of u as being the height of this surface above a plane. So if we look at the plot on the left, we can see we've got our function u of xy here, and for each point, xy, we can go up and say this is the height of our function u at that point. And we map that out for our whole domain, and we get this 3D surface, which can be projected down onto the xy plane, and it leads to our projection, which you can see is our domain of the function. It's our possible values of x and y, and they produce our 3D surface u. It's often helpful to visualize our surfaces using contour lines, and this is when our u of xy is constant. So for every value on our plot here, where u is a constant number, so if this value up here was 5 for example, every point on our surface going all the way around here like this has a value of 5 in the u direction. So if we look at our example of u equals x squared plus y squared minus 5, it would be this sort of quadratic shape, but all the way around it's a surface going in 3D. And the contour lines for it are perfect circles. If we now take this arrow to mean we're looking from the bird's eye view, like we did for our domain here, we'll see we have circular contours. We now look at some spatial rates of change. If we start at point P on our u surface, and that point is defined by xy, and we move a small distance, delta x, which is equal to h, and therefore we move to this new point, q, of x plus h, and we keep y the same, so we're only moving in the x direction by a small amount, delta x or h. Similarly to how we've defined a derivative before, we can say that du by dx, and this d is our partial d, which we'll get onto, but this equals the limit as h tends to 0 of our function u of x plus h, and we're keeping y constant, minus where we started at our point P, divided by the difference in our x coordinate, which is now going to be just h. And this is equal to the rate of change of u with respect to x. So this notation can just be written as we already have, du by dx, but this is also equal to du by dx, and this is just notation, at constant y, that's what that bracket will mean, and you can also say du by dx at constant y, like that. And then similarly, if we look for, if we're moving only in the y direction, we'd have our p of xy transforming to q of x y plus k, where k is our delta y. And this will give us a similar expression. And again, we can have other notations, so this is also equal to du by dy at constant x, or du by dy at constant x, like that. So in each case, we're either keeping y constant, and we get our partial derivative with respect to x, or we're keeping x constant, and we're getting our partial derivative with respect to y. I just wanted to make clear that this q here and this q here are not the same point. One is moved in the x direction, one is moved in the y direction. So to perhaps make that more clear, I'm renaming the second one as r. So if we had this on some plot where this direction is x and this is y, we'll have our point P here, and then when we move in the x direction, we'll get to our point Q. When we move in the y direction, we'll get to our point R. And each of these distances is going to be h and k, which is delta x and delta y respectively. Of course, we can also consider higher derivatives, so if we were going to take a double partial derivative of u with respect to x both times, we have dtu by dx squared. That will equal partial d by dx of partial du by dx. I avoided naming this other notation, but you can write this as u and then subscript xx, and obviously before that means this would also be u of x and this will be u of y. But I find this is overcomplicating at this point. These notations of subscript, and then you will also see a superscript like this, will come much later on in things like general relativity and advanced classical physics, as this is Einstein notation. And for now, I'll try and avoid using them, but I'm just showing this can be used. So another higher derivative we might consider is the double partial derivative of u with respect to x and y, which will equal partial d by dx of partial du by dy. Note the order here is partial dx and then partial dy. Obviously for double derivative up here of with respect to x, we can do the exact same thing with y, and we'd have some u y of y like that, but I'm not going to bother writing that out. And so this second example will be u of xy in our Einstein notation, or this other notation of writing these partial derivatives. If we consider an example, u equaling x squared sine y plus y cubed, we can find that our partial derivative with respect to x is equal to 2x sine y. So all we've done here is take a derivative with respect to x, and you can see this is going to be a constant, so when you're differentiating with respect to x, that will become 0, and then we're just differentiating that x squared, and we get 2x sine y. Now if we do du by dy, partial derivative, we'll get x squared stays the same, and we're then differentiating sine y to get cos y plus 3y squared. And then if we take that further for our higher derivatives, so we'll have our dtu by dx squared equals d by dx of du by dx, and so that's just going to be 2 sine y. We can differentiate that to x and we get 2. And then if we look with respect to y, we get dtu by dy squared equaling minus x squared sine y plus 6y. And now if we wanted to do our combined terms where we have one partial derivative in terms of x and one in terms of y, we can do our from our du by dx. So if we do d by dy of du by dx, i.e. d2u by dy dx, we'll have 2x cos y. And then similarly, if we do d by dx of du by dy, and we have d2u by dx dy, that's also going to equal 2x cos y. In the first example, we're just differentiating with sine y, and we get 2x sine, and we get 2x cos y. And then in the second one, we're now going to be differentiating this x squared with our cos y staying constant like that. And this 3y squared again will be a constant when differentiating with respect to x, so that will go to 0. And so we can see that this leads to the result that d2u by dy dx is equal to d2u by dx dy. And it turns out this is actually a general property of partial derivatives. It doesn't matter the order in which we do our partial derivatives, as they are independent variables one another. So it turns out any combination of partial derivatives in terms of x and y, it doesn't matter as long as you've done the same number of each. So if we use our shorthand notation, because I don't want to write it all out, we could say partial derivatives like x, y, then x. If you did all of those, that's equal to u of y, x, y. So we've got 2 y's and then 3 x's like that. Those are equal to each other. And so this is a very general case for no matter how many times you differentiate, as long as you do the same number in each of your independent variables. So now if we consider another example where u is now a function of x and t, and it's equal to a sine x minus ct, where a and c are positive constants. If we work out our du by dx, we're going to have a cos x minus ct. And now if we find our dtu by dx squared, we'll have minus a sine x minus ct. And then we can look at, well, du by dt. What's that? It's going to be minus a times c cos of x minus ct. And then this is going to be minus a c squared sine x minus ct. And so if we compare our dtu by dx squared and dtu by dt squared, we can see the difference is a factor of c squared. So we can write that this actually leads to dtu by dx squared equals 1 over c squared times dtu by dt squared. And this is a very important equation in physics. It's the one-dimensional wave equation, which you'll see a lot throughout physics. And our function, u of xt, is actually a solution to that equation. It satisfies our 1D wave equation. So for our last example, u equaling arctan of y over x, if you work out, similar to what we've done here, our du by dx and then dtu by dx squared, and do the same with respect to y, it ends up that it actually satisfies something called Laplace's equation. And this is a second order linear partial differential equation. And all those words will make much more sense when we get to later portions of the course. And this is two-dimensional, and it's represented by this nabla squared u. This upside-down triangle represents that we're going to take the derivative with respect to x and y in this case, because our u is a function of x and y. If this was 3D, it would mean that we'd be taking all of the derivatives with respect to x, y, and z, and so on. But because this is 2D, we only have x and y, we're going to be looking at dtu by dx squared, and it's a double differential because of this squared up here. And you add all of our partial differentials together, and you get dtu by dy squared. And Laplace's equation is just saying that this is equal to 0. And our function u equals arctan y over x satisfies this, Laplace's equation. Today, we've learnt about what partial differentiation is and some associated definitions. In the next video, we'll be looking at what a total differential is and how that relates to partial differentials. So if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.